Welcome for joining this presentation on our paper titled A Novel Approach to Tracing Safety Requirements and State-Based Design Models. I'm Munif Alinazi from University of Cincinnati. This work is a collaboration with my advisor, Professor Nanyu, and our industry partner, Nuha Sabulainen from Danfoss Drive. Our paper overcomes the problem of the low precision challenge that faces automated requirements traceability. Traceability, which refers to the ability to follow the life of requirements, has long been recognized as an important component in building safety-critical systems. Traceability plays an essential role in assuring that software and systems are safe to use. With the use of model-driven engineering being on the rise, state-based models become larger and more complex. This presents a significant challenge for design reviews, where the inspector may have to browse through the models and manually analyze large number of links between safety requirements and design models. Researchers therefore have proposed many techniques to automatically establish and evolve trace links. However, automated requirements traceability still faces the low precision challenge due to a large number of false positives being returned and mingled with the true links. State-of-the-art approaches show a precision of only 29.4%. To overcome this challenge, in this study we present a mutation-driven method built on the novel idea of intentionally generating many false positives from a state-based model and then leverage model checking to check whether a safety requirement is met in them in order to identify the actual slice trace. Before describing our approach in detail, we define a traceability information model that underlies our work. TIM explicitly records what artifacts are important and what others are not under the current traceability consideration. As Major and his colleagues state, defining TIM early in the project is key to the development of safety-critical systems. Thus, this figure presents our TIM, while the safety requirement or property presents the tracing source. The tracing target is a state machine diagram which is typically used in SysML models. I'd like to mention here that this TIM delineates the focuses of our work. For example, it's beyond our current scope to trace a single safety property over multiple SMDs or over different types of SysML models like internal block diagrams or activity diagrams. Now I will present in brief the steps of our approach. At first, we export the SMD under test into an XML file, and then convert it to an event log. The safety property P under test is transformed into LTL formula. After proper configuration, we perform model checking with the help of ProAm tool, especially its LTL model checker. If failed, we then have to refine either the safety property P or the design model M. The main reason of this step is that if the model checker fails, then the model already doesn't satisfy the requirement, so no tracing should be performed. Once the property is met, then this leads to the first step of our approach, which is creating mutants of the SMD. These mutants are based on the mistakes commonly made in SMD modeling. We surveyed the literature to identify these mistakes and identify 15 mutation operators. We developed a script to modify the XMI by leveraging some of these identified operators. All these generated mutants are now converted to an event log. We leverage LTL checker within process mining. Our model mutants are good fit to process mining in that the flexibility of each mutant is restricted to a single symbol and syntactic change over the original SMD. In particular, each mutant is defined with a case ID in the event log. Once a model checking is performed, we are interested in obtaining two models, one underlying all the killed mutants and the other one for all the survived ones. We marked a mutant is killed if its model checker fails, otherwise it survived. These mined mutants are in a form of matrices. Recognizing the difference between the killed and the survived mutants allows our approach final step to identify the traceability link. This figure presents our algorithm to slice our design model M by contrasting killed and survived models. To maintain a high recall value, our tracing algorithm initializes L with all the states of M. We then check the pair of states having only positive correlation in the killed mutants. For each of the selected state pairs, we mark both states with remove if the two conditions shown in line number 3 are met. That is, the correlation score of the selected pair in K is greater than threshold K, and that the difference between the correlation score of each selected pair in K and that in S is larger than 1. Having made the marks on the examined states, we remove from L those state received marks and only remove marks. The candidate traceability link returned by our algorithm lead to recall equal 100% and precision equal to 75% using the running example in our paper. To evaluate our approach, we set the following questions. How accurate is our proposed mutation-driven traceability approach? While overcoming the low precision challenges our primary goal, we do not want to hurt recall. Thus, our measure includes F1, which is the harmonic mean of recall and precision. The second research question is how to best operate our approach in practical settings. We investigate here the impact of threshold K value on tracing accuracy. Discovering an optimal threshold range is crucial in our approach since it's a key condition to identify removable states. For accuracy comparison, we use backward slicing and forward slicing algorithms as baselines. Our experiments are carried out in the context of two subject systems from the automotive domain, namely adaptive cruise controller and power systems. The answers to research question 1 are summarized in this table, where the average recall, precision, and F1 values are reported. Our approach doesn't rely on structural dependency like in backward slicing, and therefore doesn't face the challenges of which direction to slice and when to stop slicing. As a comparison with these approaches, using model checking to verify the SMD and its mutants improve the average precision by over 10% without hurting recall at 100%. To answer the second research question, we calibrate threshold K and measure how it impacts precision. The results suggest threshold K range of 0.6 to 0.8 further improves the average precision to 75.4 for ICSE and 72.8 for PS. To conclude, a mutation-driven approach to tracing safety requirements and SMD in SysML modeling is proposed. Experimental results show the precision improvements. The novelty of our work lies in our creation of many imperfect tracing targets, leading to new ways of establishing traceability links. In the future, we plan to expand the TIM to handle more complex requirements, include different types of diagrams like activity diagrams and internal block diagrams, and improve the usability of the model slices.